In this video, I bust a few myths about electricity. The first myth is that positive electricity is the opposite of negative electricity. Before Benjamin Franklin, it was thought that there were two types of electricity. If you rubbed amber with wool, that wool would develop a property they called electricity, after the Greek word for amber, which was electron. That property was that it would tend to attract small particles such as dust. Also, if you rubbed glass with silk, it would also develop electricity. But the interesting thing was, if you took two pieces of electrified amber and held them near each other, they would repel each other. The same thing would happen with two pieces of electrified glass. But if you brought a piece of electrified amber and a piece of electrified glass close to each other, they would attract each other. So it was thought that there were two types of electricity. There was resinous electricity, which developed when you rubbed amber with wool, amber being fossilized tree resin, and vitreous electricity that you got when you rubbed glass with silk, vitrium being the Latin word for glass. And the other interesting thing happened is that if you let that electrified glass touch that electrified amber, the electricity would disappear. Benjamin Franklin proposed that maybe there's only one kind of electricity, and since by this time they had discovered that electricity was a fluid and that there was a property called electrical pressure, maybe one of the types of electricity was simply the same electricity under a higher pressure than the other type of electricity. Let me demonstrate this. I'm going to take a breath. What did I just do? I expanded my lungs, making the air molecules go further apart, and so they interacted with each other less, creating less air pressure. And so the higher pressure outside went in my windpipe and filled my lungs. Now I'm going to breathe out. Now I collapsed my lungs, making more pressure than the outside, and that forced the air out. Did I create a different kind of air in my lungs when I breathed in than when I breathed out? No, it was the same kind of air under different kinds of pressure. And so Franklin proposed that electricity was the same thing, that it was a fluid that would move from one place to another because one had a higher pressure than the lower pressure. So if vitreous electricity had a higher pressure than the resinous electricity, it would flow from one to the other until they equalized. Now we know that voltage is relative, that positive is not the opposite of negative, but a negative voltage is just a voltage that's lower than some other voltage. Let me demonstrate this by drawing some batteries on my board. Now I'm going to use my black pen and my red pen to simulate the leads of a voltmeter, and we're going to put them here and see what voltages we read. So I'm going to start by putting my black pen at the negative side of this battery and my red pen at the positive side. And so that's like the black lead of my voltmeter here and my red lead there. What do you think the voltmeter is going to read? It's going to read positive 5 volts. What's going to happen if I reverse them? I'm going to put the black lead at the positive and the red lead at the negative. And it's going to read negative 5 volts. Did the voltage change? No, only my placement of my leads changed. So I didn't change the electricity, I only changed the placement of my leads. So if my red lead is at a higher voltage, I get a positive voltage. If my red lead is at a lower voltage, I get a negative voltage. Now let's put the black lead here. Let me draw it there so I can just do this a little easier. Now what's going to happen if I put my red lead here? I'm going to read negative 5 volts. Now what happens if I put my red lead here at the top of this other battery? Well, it's just another 5 volt battery. Black lead at the negative, red lead at the positive. It's going to read positive 5 volts. So positive 5 volts. What's it going to read when I put the red lead here? Well, they're at the same voltage, so it's going to read 0. A voltmeter tells you the difference between two voltages. And so if I put my red lead here, there is no difference. And so it says there's 0 volts because there's 0 difference. Now if I put my red lead here, it's going to read negative 5 volts. So positive 5 volts, 0 volts, negative 5 volts. But if I put my black lead back at the bottom, what's going to happen? Now if I put my red lead here, I'll read positive 5 volts. What's it going to read when I put it here? Well, if you put batteries end to end, the voltages just add together. So I get positive 10 volts. Positive 10, positive 5, what do I read here? 0. Now let's put the negative lead up here at the top. Now as I move my positive lead around, I'm going to get 0 volts, negative 5 volts, negative 10 volts. Have these voltages actually changed? No. All that's changed is where I put my meter. So the way a voltmeter works is I take my black lead, and wherever I put that black lead, that will be 0 volts. So 0 volts is not the absence of voltage. It's only wherever I place the black lead of my voltmeter. So if I place it here, I have 0 volts at the bottom, 0 volts, 5 volts, 10 volts. If I put my lead here, I get minus 5 volts, 0 volts, plus 5 volts. And if I put my black lead here, I get 0 volts, minus 5, minus 10. So negative voltage is not the opposite of positive voltage. It's just telling me that I'm reading a voltage that's lower than some other voltage, which happens to be where my black lead is. The next myth is that electricity travels at the speed of light. Well, let's do a simple calculation to see if that is true. Let's take a 12-gauge wire and push 1 amp of current through it. Now, we need to define what an amp is. Well, like any other kind of flow, electrical current is measured in some kind of volume over time. For example, if we're measuring water flow, we might measure that in gallons per hour. Or if we're measuring gas flow, such as air, we might measure that in cubic feet per minute. Well, in electricity, we measure an amp as a certain number of electrons passing by a certain point in a second. And that number of electrons is, need a lot more zeros. Still need more. Let's see if I got the right number here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So we have this many electrons passing by a point every second when we have 1 amp of current. That is an awful lot of electrons. But let's see how fast they're moving. Starting with our 12-gauge wire, well, 1/1000th of an inch of this 12-gauge wire has 1 amp's worth of electrons packed into it. So there is 1/1000th of an inch. And there are 6.24 times 10 to the power of 18 electrons packed into that 1/1000th of an inch of wire. So to move 1 amp's worth of electrons 1 inch through this wire is going to take 1,000 seconds, or more than 16 minutes. So 16 minutes to move 1 amp of current through 1 inch of 12-gauge wire. That's incredibly slow. So why, if I have a simple circuit, such as a battery, that's the electronic symbol for a battery, a switch, and a light bulb, when I throw the switch, how come that light bulb lights instantly? If it's an inch away from the switch, it should take 16 minutes before the electrons get from the switch to the light bulb. But we know it lights right away, so what's happening? Well, let's take a look at what's happening in the wire. Let's imagine that our wire is a pipe full of marbles. And I'm going to take another marble and push it into the pipe. What's going to happen? It's going to push on all of these marbles, and then that marble is going to come out. Now, did this marble go all the way through the pipe? No. One marble went in, and instantly another marble came out. It wasn't the same marble that went in. So this marble does not have to go all the way to the end of the pipe before we see another marble come out. We put one marble in this end, and another marble comes out that end. And electricity works the same way. That wire already has gazillions of electrons in it. And so when we push 1 amp of current into one end of the wire, a completely different amp of current comes out the other end. So this happens instantly in the blink of an eye, right? Well, not quite, because even though these marbles are made of glass and glass seems pretty solid, there is some elasticity. And when I push this marble in here, it does distort it a little bit, squeezes it a little together a tiny bit, and it takes a tiny bit of time for that to recover its round shape and impart its energy into the next marble, which does the same thing. And it distorts its shape a little bit, and then when it recovers its shape, it pushes its energy into the next marble. So it takes a little bit of time between when I first start to push this marble in and the marble at this end begins to move. How long does that take if it's marbles? Well, if this pipe were 1 kilometer long and all of these glass marbles were in contact with each other, that wave of energy that starts when I push this marble in would travel through these marbles at about 4 kilometers per second. So it would take about a quarter of a second between the time I push the first marble in and all the marbles are moving, and then this marble can come out. Electricity works the same way. If I push an amp's worth of electrons in one end of a wire, it does take a while for the wave of energy to propagate through all of the electrons and get them all started moving. That would travel at the speed of light, except that the electrons interact with the molecules of copper in the wire, and that does tend to slow things down a bit. And there are other electrical properties that slow it down even more. In your typical wire, you can expect that wave of energy to travel at about 60% of the speed of light. In some wires, such as Ethernet cables for networking, it actually goes more like 50% of the speed of light. The highest speed is obtained in antennas, where we have wires that are going in opposite directions in space away from each other, where we have the least amount of interaction between the two wires, where the speed might get up to 98% of the speed of light. But the electricity does not travel at the speed of light, and except for antennas, it doesn't even come very close. So your typical wire might be about 60% of the speed of light. The next myth is that it's not voltage that kills, but current that kills. This is like saying, well, the tiger didn't kill him, it was the tiger's teeth. Well, the tiger's teeth aren't going to do much damage without the tiger behind it. And that's the same thing with electricity. Current is not going to exist if there is not voltage to push that current. Now, I personally have been hit with as much as 100,000 volts, and not only lived to tell about it, it didn't feel like that much, maybe like a pinprick. This was with a Van de Graaff generator that produced 100,000 volts, but had no volume of electricity behind it to back that up to create the current that was necessary to cause some damage. On the other hand, you can be killed with as little as 50 volts if there's enough volume of electricity behind that to develop the current needed to do the damage. It takes anywhere from 50 to 101 thousandths of an amp to kill somebody. So that's a very tiny amount of electricity. It takes about 6 milliamps, or 6 1,000ths of an amp, directly across the heart to stop it from beating. And to get that 6 milliamps across the heart, it takes anywhere from 50 to 100 milliamps across the whole body. But although we concern ourselves with the number of amps it takes to stop the heart, if we don't have the voltage, there will be no amps. So the concern is, do I have enough voltage to push enough current through me to kill me? Then once I have enough voltage, is there enough volume of electricity? Are there enough electrons behind that voltage to develop the current necessary? But we need voltage first, then comes the current. I saved the next myth for last because it's actually dangerous. And that myth is that electricity always takes the shortest path to ground. To illustrate this, let me draw a generator. This represents the power plant that is supplying power to your house. And let's make it a nice even 100 volts. Now, in America, that would be 117 or more volts. In Europe and most of the world, maybe 240 volts. But 100 volts here just to make an even number. And here are the wires that supply power to your house. The hot wire and the neutral wire. And somewhere along the line, the neutral wire is connected to the earth or to ground, and so we'll draw that in here. Now let's say we have some kind of electrical equipment, maybe a power drill or a heavy light or something, and that has basically a resistance of 10 ohms. Now we divide 10 ohms into 100 volts. That tells us that we have 10 amps flowing through this resistor. That's not enough to blow the circuit breaker. It's a heavy load, but we've got some current going through there. Now I'm going to come along and I'm going to touch that hot wire. So here I am, Mr. Stick Figure, and I'm also connected to the ground. So I'm connected to the neutral wire here too, so I'm creating a circuit. Let's say it's a humid day and my skin is wet and I'm making good contact, so I have a fairly low resistance myself of maybe 2,000 ohms. So we have two possible paths here. We have a 10 ohm path and a 2000 ohm path. No problem, I'm safe because the electricity is going to take the shortest path to ground, which is 10 ohms, and so I'm safe. Is that correct? No, I'm not safe. There is still 100 volts across this. That's the nature of what's called a parallel circuit. Whenever we have multiple paths, that is called a parallel circuit. So there's one path here, another path here. That's a parallel circuit. One of the main rules of a parallel circuit is that the voltage is the same. So there's 100 volts here, and there's 100 volts here. I still have 100 volts across my 2000 ohms, and that, divide 2000 ohms into 100 volts, and that's going to give me a current of about 50 milliamps, which is enough to kill. So why do we ground equipment? To make them safe. After all, I just showed that making a shorter path to ground doesn't really make things any safer because the electricity will take whatever path it can find. It'll take the shortest path and it'll take the longest path. And what really matters is what is the resistance to see how much current you get. So why do we ground things? How does that make things safe? Well, let me illustrate that this way. This is a redrawing of my diagram giving a more realistic situation where I'm using a power tool or something. We have my 100 volt generator at the power plant. There's my 10 ohms for my power tool. It's got a metal case around it which I'm touching, but that metal case is connected to ground. And for good measures, let's just say that that ground wire has 1/10 of an ohm of resistance. So I'll draw that as a resistor here. Now that's a lot more resistance than we really would have, but it makes the numbers easy for this illustration. And one other thing I've added is 1 ohm of resistance here. This is actually part of my generator and my power delivery system. Everything has resistance. So my generator actually acts like a generator with some resistance in series with it. And I've made that 1 ohm, which is way too high, but it will help to illustrate this problem. Now remember, whenever you have current going through a resistance, you're going to get a voltage difference from one side to the other. Again, it's like blowing through the straw. If I pinch it down and blow through it, I get a higher pressure where the current encounters the pinch and a lower pressure on the other side. It can be reversed, like I can be sucking on it, and once again I get a lower pressure on the side where the current is coming out and a higher pressure where it goes in. So in electricity, we have a higher voltage where the current enters the resistance and a lower voltage where it exits. Now this is alternating current and it's going back and forth, but we can use DC to illustrate how things work. So a higher voltage here and a lower voltage here. This is at 100 volts and it can't change because of the nature of the generator. So we have to have a lower voltage on this side. So we lose about 10 volts going through this resistance, leaving us with 90 volts here. Now let's see what happens if we have a fault and this hot wire somehow comes in contact with my metal case for my drill. Now I have 90 volts touching the drill case, I'm touching the drill case, and ground, so I have 90 volts across me, and 2000 ohms, definitely enough to be dangerous. Let me redraw this as a circuit diagram because it's getting a little cluttered here and I think I can make it a little more simple to show what's going on. So here's my generator, my 1 ohm that's part of the generator. Here's my drill, here's my ground wire, and here I am. Now, how much resistance am I going to have together here? Well, I could do some mathematics to figure it out, but essentially I'm only going to have 1/10 of an ohm. Why? Because this is like taking a fire hose and adding a garden hose and a soda straw. They're not really going to contribute much to how low the resistance is here. So essentially altogether we have 1/10 of an ohm at this point. Now each of these resistances will take their fair share of the current because remember it's not going to be all of the current going through the shortest path to ground. Each one gets its share. The question is, will I have enough voltage across here to be dangerous to me? Let me eliminate the drill and me just to simplify things a little. So now what we have is a 1 ohm resistor and a 1/10 of an ohm resistor in series with each other. Let's see how much voltage we get across this 1/10 of an ohm. Well, we have 1 ohm and 0.1 ohm. They're end to end in series. So we add those together. So we have 1.1 ohms. And then we divide that 1.1 ohms into our voltage to find out that we're going to get approximately 90 amps. Well, that's going to blow my circuit breaker anyway, but not fast enough to save me. So how much voltage will be here, which is the voltage that I am touching, what's the voltage there? Well, with 90 amps going through 1/10 of an ohm, we're only going to get 9 volts. So I've got 9 volts at this point, and I'm touching the ground. So I've got 9 volts and 2,000 ohms. That's about 4 milliamps, well within the safety limit. So when we ground something, we're taking advantage of the inherent resistance in the system so that when we do have a short, that we get the high current through here, but the resistance here is so low that the resistance of the system overwhelms it, and I lose so much voltage going through this resistance, I have nothing left over across the resistance of my ground. Therefore, I don't have enough voltage to push the current through me to be dangerous. And now for a bonus myth. You may have actually caught this myth earlier. That myth is that 0 volts is the absence of voltage. Actually, voltage is always a differential. Whenever you measure a voltage, you're always comparing it to another voltage. One voltage is meaningless unless you have another voltage to compare it to. That's why a voltmeter has 2 probes. You put one probe at one voltage, and you put the other probe at another voltage, and it tells you the difference in voltage between the two. And if you put the red probe at the higher voltage, it'll tell you a positive voltage, and if you put the black probe at the higher voltage, it'll give you a negative voltage. When a voltmeter reads 0, all it is telling you is that the red probe and the black probe are at the same voltage. So wherever we put our black probe, that by definition is 0 volts. And our red probe will then tell us if the voltage at the red probe is higher or lower or the same. If you found this video useful and informative, please give me a thumbs up down below. It really helps the channel. And subscribe, because that not only informs you when I put new videos up, but it really helps the channel also. And a big thank you to my patrons at Patreon. I could not make these videos without your support. If you want to help me put these videos online and keep real vocational education free at vocatomy.net, you can go to patreon.com/join/vocatomy and pledge your support. And again, a big thank you to my patrons who make this possible, and a big thank you to everyone for watching.